Okay, here we go. All right. In probability, we conduct experiments. And these experiments are usually a lot different than what you would conduct maybe like in a chemistry lab or a physics lab. But a probability experiment is a process that leads to well-defined results called outcomes. An outcome is a result of a single trial of a probability experiment. An example of a probability experiment would be flipping a coin. And when we flip a coin, there's going to be some sort of an outcome. Either we flip a head or we flip a tail. Theoretically speaking, there is a small chance or a small probability that when we flip a coin, it will land on edge. But I've never seen that happen before. And so for all intents and purposes, we deem that to be negligible. So when you flip a coin, you're either going to flip a head or a tail. Now, if we have a fair coin is sometimes called an unbiased coin. A fair coin is one in which the chance of flipping a head is equal to the chance of flipping a tail. All right. If your coin is weighted in any way, then that probability or that statement is not going to be true. In which case, in order to compute probability of tossing a head or a tail on an unfair coin or a biased coin, you would have to use empirical probability to do so. You would have to look at the relative frequency of occurrence of a head or a tail in such a biased coin. But normally we assume our coins for our experiments are fair coins. They're unbiased and unweighted coins. All right, so when we flip a fair coin, what's the probability that we will flip a head? And ladies and gentlemen, when we flip a coin, there are only two possible outcomes, either a head or a tail. This is an example of a 50-50 chance. There's 50% chance that it will land heads up and a 50% chance that it will land tails down, tails up rather. We were told that probability is like percent chance. So probability and chance are pretty much the same thing. And when we compute probabilities of outcomes of experiments, it will always be a decimal or a fraction between 0 and 1 inclusive. All right. Now, we know that if there's a 50% chance of something occurring, then we can call it a decimal 0.50. All right. Now, when we compute probabilities in this course, we're not going to cite the probability as a percent. We're going to cite it as a decimal, sometimes as a fraction, but more commonly as a decimal. All right. Okay. Probability is, I like to say, it picks up where science leaves off. Now, if we're able to model a particular scientific phenomena or a phenomenon in our everyday lives according to some sort of like a function or mathematical equation, then, ladies and gentlemen, there really is no chance involved there in trying to predict what state that phenomenon is going to be in. We would just use our equation to, predict or to give us a 100% definitive idea as to what state that phenomenon is going to be in. But there's a lot of things in real life that cannot be modeled according to a mathematical equation. I'll give you an example. One example is trying to predict when an earthquake is going to occur. To date, scientists still have not come up with a definitive, concrete, 100% accurate mathematical model that can indicate exactly when an earthquake is going to occur. As a result, we oftentimes have to speak in terms of probability. So probability or chance picks up where science, exact science, leaves off and cannot deal with anymore. Okay. And there's a lot of things in our everyday lives that involve probability or chance. For instance, if you play a particular, like a lotto game or a lottery game, You have to speak in terms of the odds or the probability or the chance of you winning or losing such a game. Okay. Weather forecasting is a very complicated science, Lezaman, and I know firsthand that the mathematical models that they use to try to predict what tomorrow is going to be like weather-wise, those mathematical models are approximations of the thermodynamic and the fluid dynamic aspects of the atmosphere. And as a result, because they're approximations, that leaves the door open for error, okay? And as a result, oftentimes, especially for precipitation, we don't have an exact mathematical model that with 100% certainty will tell us exactly how much rain will fall in a particular area. We have to speak in terms of probability or chance. All right, when we conduct an probabilistic experiment, they always have some sort of a sample space. A sample space for a probability experiment is a set that consists of all the possible outcomes of such an experiment, okay? For instance, if our experiment is that we flip one coin, then the sample space will be the set consisting of the two possible outcomes of head or tail. When we roll a die, which is a six-sided cube, okay, where each side has a number on it, either 1 through 6, all right, when you roll a die, the sample space would be the set consisting of all the possible outcomes, which would be 1, 2, 3, 4, 5, or 6. If you answer a true or false question on an exam, there's two possible outcomes, either true or false. That would be the sample space consisting of those particular outcomes. When you flip two coins, okay, the sample space becomes a little bit more complicated, but nonetheless has a finite number of outcomes. You could flip a head and a head, a tail and a tail, a head and then a tail, or a tail and then a head. Those would be the outcomes of flipping two coins. So every probability experiment has a sample space. An event in probability is defined to be any subset of the sample space of an experiment. For instance, suppose we have an experiment of drawing a card from a deck of cards. The sample space would be a set consisting of all 52 cards. We could define an event for such an experiment to be that we draw an ace, or maybe the event would be that we draw a face card, which would be a jack, a queen, or a king. Or maybe the event would be that we draw a spade, which would be an ace of spade, 2 of spades, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king of spades. Okay, so events are subsets of the sample space. All right, there's two main ways of computing probabilities. There's what's called the theoretical probability method, and there's the empirical probability method. The theoretical probability method, sometimes called the classical probability method, presupposes, ladies and gentlemen, that each outcome in the sample space of an experiment has an equal chance of occurring on any given trial of the experiment. Okay, so sometimes we call this the equal likelihood model or a way of computing probabilities. Suppose we have an event E to be the event that is a subset of our sample space S, and suppose that N of E represents the number of ways that event E can occur. Okay, suppose that N of S represents the total number of outcomes that exist in our sample space. So this lowercase n represents the word number. Right? Now, the probability of event E occurring is defined or computed by using this theoretical probability mathematical rule or law here. And this notation here is to be interpreted as the probability of event E occurring. So you don't say P times E, you don't read it that way. You could read it as P of E, or you could read it as the probability of event E occurring is going to be equal to the number of ways that event E can occur divided by the total number of outcomes for the particular experiment. And the key assumption that governs this way of computing probabilities is that we assume that every outcome has an equal chance of occurring on any given trial of the experiment. If that was not the case, then we would not be using this theoretical probability way of computing the probability. Here's an example. A single die is rolled for the 3 events listed below. Without calculating probabilities, put them in order from least to most likely based on educated guess, then compute each probability. Okay. All right, ladies and gentlemen, so for classwork number 1, what I want you to do is for A, B, and C, I want you to order these based on the likelihood of these events occurring. For instance, A says, what's the likelihood of rolling a 5? B is what's the likelihood of rolling a number less than 5 when we roll a die. And event C is what's the event that we roll an odd number. Put those in order from least likely to most likely, right? Classwork number 1. All right, so we're going to try to order these from least likely to occur to most likely to occur. And does anybody want to weigh in on the situation? You feel confident with your results? Go ahead. Least likely to occur, most likely to occur. And you can just use the letters A, B, C. Okay, let's order these A, B, C in the proper order. Least likely to most likely to occur when you roll a die. And we're assuming the die is a fair die.
A, B, C.
Okay. A, B, and then C is how you label these here. Okay. Why do you say like event A that we roll a 5 is least likely to occur? What would be kind of like your reasoning behind that?
Because that's just 1 of 6.
Yeah, 1 of 6. Okay. And why would we say that C is the most likely to occur here?
Because there's 3 odd numbers on any given D6.
Okay, 3 odd numbers out of 6. 3 ways of an odd number occurring out of 6 chances. All right. B, how many ways can you roll a number less than 5? Well, that would occur if you roll a
2/3.
1. That would be like that'd be like if you roll a 1 or a 2 or a 3 or a what? 4? Okay. That can occur how many ways?
4/6 you can reduce to 2/3.
And this odd rolling an odd number was 3 out of 6, correct? Okay, so let's see if we can revise this. What should the order be here? I think there's a slight flaw in this. What should it be? Least likely to most likely. A,
C, B.
yeah, probably A, C, B. Okay. All right. Let's actually now compute the probability of each of these events occurring. And we're going to use the theoretical probability model for computing these probabilities, assuming that when we roll a die, each face has an equal chance of occurring on any given roll. That's the key assumption here. Okay, so let's go down and actually compute these probabilities. Sorry. All right, so the probability of rolling a 5 is equal to, and this is the notation, P of 5, notice that. The probability of rolling a 5 is equal to the number of ways that we can roll a 5, which is 1 way, divided by the total number of outcomes for this experiment, which there are 6 different outcomes. So we would say the probability is 1/6. If you wanted to turn it into a decimal, you could do that by dividing 1 by 6. And that's going to be a repeating decimal, which is about 0.16666. Well, exactly 0.16666 repeats. So we would call that approximately about a 17% chance. And again, if you wanted to cite this as a decimal, you would say approximately equal to about 0.17 if you round it off. Okay. All right, what's the probability of rolling a number less than 5? Well, it's denoted symbolically this way. That would be equal to the number of ways that this event can occur, and the number of ways of rolling a number less than 5, which would be 4 ways, rolling a 1, 2, 3, or 4, divided by the total number of outcomes, which is 6, 2/3. Or if you turn this into a decimal, dividing 2 by 3, you would get a repeating decimal, 0.666666, and you could round it off and call it about 0.67. In our minds, we know that to be about a 67% chance, correct, for this event occurring. The probability of rolling an odd number, that can occur 3 ways. If you roll a 1, 3, or 5, 3 ways divided by 6 total possible outcomes would yield a probability of 1/2, which is equal to 0.5 or 0.50. We know that in our minds is 50% chance. Okay. Any questions about this here? Okay. Again, that was for a fair die. We were assuming that was a fair die there. Okay, let's move on. All right, now suppose that we flip 2 coins and we want to compute the probability of flipping 2 heads, or at least 1 head, or at most 1 head. Well, what would be the sample space of flipping 2 coins here? Well, if we flip 2 coins, on coin number 1, we could flip a head, and on coin number 2, we could flip a head. That's one possible outcome. Another outcome would be what? We could flip a head on the first coin and a tail on the second coin. Or we could flip a tail on the first coin and a head on the second coin. And there's one more outcome. That would be we flip a what? A tail on the first coin and then a tail on the second coin. All right, I want you to do this for classwork number, also throw this into classwork number 1. Compute these probabilities using the theoretical probability model. Go ahead and compute those probabilities here, A through C. All right, the phrase "at least" means what? At least. In other words, if I said, let's say X is at least 3, what inequality would that suggest if I said X is at least 3? X is at least 3, for example. How would I express it as an inequality? At least 3. Well, at least suggests the greater than or equal to symbol, inequality. So if I say X must be at least 3, that's saying X must be greater than or equal to 3. That's what at least means. X could be at least equal to 3, or it could be something larger than 3. Okay. What does it mean to say at most? If I said X could be at most 3, what inequality would that suggest? X could be at most 3, at most 3. That would be saying X would be
less than or equal
to 3. Exactly. At most 3 means X could be as large as 3, at most 3, but it could also be less than 3. So it's wise to understand what those phrases mean as far as inequalities are concerned. That'll become more important a little later on. Okay. All right, let's see if we can compute these probabilities here. Let's see if we had any success using our theoretical probability model, if you will. And so what's the probability of tossing 2 heads when we toss 2 coins? Well, the sample space, again, is the set consisting of all the outcomes. Head, 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 tail, tail, head, tail, tail. So the number of ways of tossing 2 heads is equal to the number of ways you can toss 2 heads. And how many different ways can you toss 2 heads? You can toss 2 heads only one way, head, head, and a head, out of 4 possible outcomes. So your probability of tossing 2 heads for this experiment is 1/4, or 0.25, or 25% chance. But please don't cite it as a percent. We always cite probabilities as fractions or decimals between 1 and 0 inclusive. What's the probability of tossing at least 1 head? At least 1 head means we could toss exactly 1 head or more than 1 head. Well, do you agree there's 3 ways of that occurring? We could toss a head and a tail, or a tail and then a head, or then a head and a head. So there's 3 possible ways of tossing at least 1 head divided by 4 possible outcomes. The probability of tossing at least 1 head would be 3/4, or 75% chance, or 0.75. Okay. All righty. Is this making sense so far here? All right. What was the last problem? The last problem was, what's the probability of tossing, what was it? At most 1 head? At most 1 head means we could toss exactly 1 head or less than 1 head. Well, okay. So what that means, ladies and gentlemen, is to toss at most 1 head on 2 coin flips means we could toss 1 head. How many ways can 1 head occur? Well, we could toss a tail and a head and a head and a tail. There's 2 ways there. Or we could toss no heads, in which way that that would occur 1 time, tossing a tail and a tail. So there's 3 possible ways of tossing at most 1 head out of 4 possible outcomes. The answer is 3/4 for that probability, or 0.75. Okay. Is this making any sense? Computing probabilities, assuming that each outcome has an equal chance of occurring on any given trial of the experiment, using this theoretical probability model. Are we all good on this way of computing probability so far? All right. Ladies and gentlemen, there are things that are always true about probabilities. Number 1, When we compute a probability of an event occurring, it can never be a negative number. Okay. So whenever you compute a probability of any event for any probability experiment, it will never be a negative number. Number two, probabilities are never greater than 1. So you'll never compute the probability of an event and it being like equal to 2 or 3 or 4. Okay. Number three, when an event can't possibly occur, its probability is equal to 0. When an event is certain to occur, the probability is equal to 1. All right. So events that will never occur have a probability of occurrence of 0. Events that are certain to occur and will occur have a probability of 1, known in our minds as 100% chance. All right. And of course, an event that has an equal chance of occurring would be 50-50 or 0.50 or 50% chance. Okay. That makes sense, sir? So those are all important requirements for probabilities. This is also important, especially when we get into probability distributions. If you add the probabilities for every outcome in the sample space, the result must always be equal to 1. What is that saying? Well, suppose that we roll a die, a fair die. The sample space will be the space consisting of 1, 2, 3, 4, 5, and 6, correct? All right. Liz, what's the probability of rolling any one of these numbers, assuming it's a fair die? The probability is in each case what? 1/6, correct? So what this last important requirement is saying for probabilities is that when you sum up the probabilities of the occurrence of all outcomes in a sample space, the sum of those probabilities has always got to be equal to 1. And that makes perfect sense why that would be the case, because think about it. There is a 100% chance, do you agree, that when you conduct an experiment, that one of the outcomes in the sample space must happen. There's a 100% chance that one of the outcomes is going to happen. And so this makes sense of what this is saying here. Okay. Any questions about those requirements or probabilities? So bottom line is this: when you compute the probability of some event E occurring, it's always got to be a probability between 1 and 0. It'll never be anything larger than 1. It'll never be a negative number. Okay. It's got to be in an interval. All right. Now this is very important. And this comes in handy when computing more complicated probabilities. It's called the complementary rule. For any event E, we say event E prime lays on. You see this little prime symbol on E? That's called the prime symbol there. We read that as E prime. If E prime is the event that E does not occur, then lays on when we run into this very important rule in probability. It's called the complementary probability rule. And this rule says the probability that event E will not occur is always equal to 1 minus the probability that event E will occur. Okay, let me give an example. Suppose I define event E to be that a light bulb is turned on. What would be the complementary event then? The complementary event to an event is the other side of the fence, so to speak, lays on. So to say a light bulb is not on is to say that it is what?
Off.
Off. Okay, so if event E is the event that a light bulb is in the on state, then the complementary event, denoted as E prime, is the event that says that the light bulb would be in the off state. It's got to be one of these two. And therefore, the probability that a light bulb is off, ladies and gentlemen, would be equal to 1 minus the probability that the light bulb is on. And assuming that each of these outcomes has an equal chance of occurrence, we would call this 1 minus 0.5, or we would call this 0.5. Right? So there's a 50-50 chance that the light bulb is either on or off. We'll assume there's no such thing as an intermediate state, like half on, off. No, that don't exist. It's either light bulb is on or it is off. Okay. So you could think of like an event and its complementary event as being like binary events, if you will. One of two opposite states. Okay. Computers, ladies and gentlemen, are binary machines. The componentry on board a motherboard, circuit board of a computer, those components are usually either in one of two voltage states, either a high voltage state or a low voltage state. And computer scientists have coined those as being like either a 0 or a 1. Okay, a 0 or a 1 state. All right, so those are binary machines. So events and their complements are like binary complements. Okay, they're the opposites of each other. All right, for instance, suppose I define event E to be that I roll an odd face on a die. What would be its complement, E prime? Anybody? What's the complement to the event that I roll an odd face on a die?
Evens.
That I roll a what? If I don't roll an odd face, I roll a even face. Agree? Okay. All right, here's another example. Suppose I define event E to be that I select a face card from a standard deck of cards. What would be the complementary event to that event? The complementary event of event E being that I select a face card from a deck of cards would be saying E prime is equal to what? What's my complementary event? Of selecting a face card from a deck of cards. Well, the complementary event denoted as E prime would be that I do not select a face card from a deck. Another example, event E is that we flip a head on a coin. What's the complementary event E prime? We flip a what? We flip a tail. Okay. All right. Here's a good example here that utilizes complements. Of the next 32 trials on the docket in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, 9 are property crimes. If jurors are assigned to trials randomly, what's the probability that a given juror won't get a homicide case? Find the probability using both the formula for theoretical probability and the formula for complements. Then compare the two methods. All right. So we have 32 trials coming up, correct? 5 are what? Homicides, 12 drug related, 6 are assaults, and 9 are property crimes. What does 5 plus 12 plus 6 plus 9 add up to? What do you think they should add up to? Well, they should sum up to 32, correct? All right. Now, in order to compute this probability, ladies and gentlemen, that a given juror won't get a homicide case, we would use our probability rule. And what are the number of ways of not having a homicide case? In other words, how many of these cases are not homicide? Well, that'd be 12 plus 6 plus 9, which is to say 27 of the 32 cases are not homicide, divided by the total number of cases. That would be the probability that a juror will not be selected to a homicide case. Another way we could compute this probability is to use our complementary probability rule. That is to say, the probability that a juror will not be assigned to a homicide case is going to be equal to 1 minus the probability that they will be assigned to a homicide case. So how many ways can you be assigned to a homicide case? Well, how many homicide cases are there of the 32 cases? There's 5. Notice 1 minus 5 over 32 is equal to 27 over 32. So both ways of computing the probability that a juror will not be selected for a homicide case yield the same probability of 27 over 32. Whether you want to compute it this way or use the complementary probability rule and compute it this way. All right, both ways work. Any questions about that there? Okay. All right. The other way of computing probabilities, ladies and gentlemen, is called the empirical probability rule. It's based on observed frequencies of what has happened in the past. That is, the number of times a particular event has occurred out of the certain number of trials. This is how we would use this model to compute probabilities. The probability of some event E occurring would be equal to the observed number of times an event E has occurred in the past divided by the total number of trials we conducted the experiment. Okay. So sometimes this empirical probability model is called the relative frequency way of computing probabilities. The relative frequency way. For instance, suppose that I go to a basketball court and I stand at the free throw line and I shoot 10 balls at the basket. Suppose of my 10 shots, I only make 3 of the 10 shots. What then, ladies and gentlemen, would we use for a probability of me making the 11th shot? We would probably base that on what's happened on the previous 10 shots. Do you agree? And we would say, well, the probability of me making the 11th shot would also be what? Would be what? 3 out of 10 chances, or a 30% chance of making the 11th shot, based on what's happened on the previous 10 shots. This is called a relative frequency, or the empirical probability way of computing these things here. It's based on observed relative frequencies, okay? Here's an example. In a random sample of 500 people, 210 had type O blood, 223 had type A, 51 had type B, and 16 had type AB. All right. Let's see if we can answer these questions. What's the probability that a randomly selected patient can receive only one type of blood? B, if an accident victim has type B blood and an EMT on site is the only person willing to donate blood, what's the probability that it will be compatible with the victim? All right. So in C, if a person with type A blood gets a transfusion, what's the probability that the donor had type O? Finally, D, what's the probability that randomly selected donor's blood can be given to patients of more than just one blood type? All right, to help us compute these probabilities, we're going to make what's called a frequency table, frequency distribution table. Notice of all the people that we surveyed, how many had type A blood? I think there were 223, correct? Okay. 51 had type B blood, 16 had type AB blood, and 210 had type O blood, for a total of 500 people that were surveyed. Now, what's the probability of randomly selecting one of these people out of the 500 and them having type O blood? That would be equal to the number of people that had type O blood, 210. That's the frequency of type O blood people, divided by the sum of all the frequencies, which is 500. So there's a 42% chance that we'll select somebody at random and they would have type O blood. That's the empirical probability way of computing this here. What's the probability that a person randomly selected would have type O or B blood? Well, how many ways can type O or B blood occur? Well, type O can occur 210 different ways, and type B can occur 51 different ways. So what's 210 plus 51? That's 261 different ways that we could select somebody with type O or B blood, divided by the total number of people that were surveyed, 500. There's about a 52% chance that we will randomly select somebody with a type O or B blood. Now, C, in order for blood to be compatible with type A patient, the donor had to be either A or O. I didn't know that. In order for blood to be compatible with type A, they have to be either A or O. I just learned something today. So O will also be compatible with A. So how many ways can we select somebody with A or O blood? Well, there's 210 ways of selecting somebody with O blood. There's 223 ways of selecting somebody with A blood. So you add those together, 223 plus 210 would give you 433 different ways of having the donor be eligible. Now, if the donor wasn't A, then they must be what? O, which is a frequency of 210 over 433. Let's see here. Let's see. Type A blood, A or O. So 433. Donor wasn't A, they must have type O, which is a frequency of 210. What was that question we're being asked here? If a person with blood type A gets a transfusion, what's the probability the donor had type O? Okay, I'm sorry. They want to know the probability that person randomly selected as type O blood. All right. Well, we didn't even have to go through, all of this here. We know that there's 210 out of 500 people that have type O blood. So all we had to do is just take 210 divided by, well, now wait a minute here. Let's read that again. If a person with blood type A gets a transfusion, what's the probability the donor had type O blood? Type O blood. Okay. There's an assumption here in this problem that's not really being stated as clearly. So this is like ill-defined, this question here. It's assuming that if we're going to give a transfusion to a type A person, then we would know that either A or O is compatible with A. Okay. So that we could use a person with type A blood or O blood. That would be compatible with this person that requires type A blood. Knowing that, of the 433 eligible donors, because there are 433 eligible donors, because there's 223 that have type A, 210 that have type O. Of the 433 eligible donors, what's the probability that they will be of type O? And that would be 210 out of 433. Okay. This question here is somewhat, this is ill-defined though. They should have been a little bit more clear on this question here. So don't worry about this. I'm not going to give you one as vague as this. If I give you a probability question, it'll be very explicit as to what I want you to do. This one is very vague. They left out some key assumptions here. They should have left to put in the wording here. All right, for D, find the probability that a randomly selected donor's blood can be given to patients of more than just one blood type. There's only one group whose blood can be donated to just one type. Do you agree, Liz? I'm going to be just what? A, B. So the question is really asking us to find the probability of that a random donor not belonging to blood type A, B can be used. Well, we can find the probability of not being of type AB by subtracting the probability that our donor is of AB from 1 using the complementary probability rule. So the probability that a donor is not type AB, the difficult way of doing that problem would be to add 223 to 51 to 210 and divide that by 500. But the easier way, Lizone, is to use the complementary probability rule, which is to say the probability of not having a type AB donor is equal to 1 minus the probability of having a type AB donor. And how many type AB donors do we have? I think there were 16, is that correct? 16 out of 500? Subtract that from 1 or 500 over 500, you get 484 out of 500. About a 97% chance of not having a type AB donor there. Okay. All right. Okay, so what we've seen here so far is we've seen two ways of computing probabilities. The theoretical probability model, which is the equal likelihood model. And, ladies and gentlemen, we've seen the relative frequency way of computing probabilities, the empirical way, where probabilities are computed on what's happened with a relative frequency of occurrence of an event in the past. Let's see if we can go have some fun with our textbook a little bit here. We're in section 10.1. We only did one classwork here, so we'll be adding on to this classwork. Okay. And as always, please do take the time to look through some of these examples here. They do give some examples here and here that were not covered in the lecture there. Okay. All righty. Okay, so let's see if we can do a couple problems here. Okay, ladies and gentlemen, number 11 here. We'll just do this as a class here. Is 3/4 a valid probability of some event? Is 3/4 a valid probability?
Yes.
Yes, it is. It is a fraction whose decimal would be 0.75. If you were to divide 3 by 4, that is a valid probability. Number 13, is that a valid probability? -1/2.
No.
Why
No.
not?
Because it's negative.
Yes, you can never have a negative probability. That is not a valid probability. That's not happening. Okay. Is number 15, 41 over 40 a valid probability? 41 over 40. Is that a valid probability?
I'm going to say no.
Yes, you are correct. Why did you say no? Just a 50-50 guess, or?
It's because, well, the one on top is more than the one below it.
That's right. If you were to turn this in to a mixed number or a decimal, you would discover that you have a probability that's greater than 1. This is a no-no. So therefore, ladies and gentlemen, that's not a valid probability. How about 14? Could a probability of an event be 0? Is this valid? Is that possible?
Yes.
That certainly is possible. That's like saying, what's the probability of a Martian on planet Mars getting an engineering job here on planet Earth? You know what I'm saying? Well, for one thing, the Martian probably doesn't even know the job exists, may not even know where the planet Earth is. We'd probably call that 0%. Okay. All right. Is number 16 valid? 40 over 41. Is that a valid probability?
Yes.
Yes. Notice it looks very similar to 41 over 40, but there's a difference. 40 over 41 is less than 1. 41 over 40 is greater than 1. So yeah, 40 over 41 is a valid probability. This is interesting. I'm curious to see what your author says about this. Is this a valid probability, ladies and gentlemen? Based on how we define probabilities to be in this lecture, what do you think? Is that a valid probability? Based on how you've seen it defined in this lecture. What do you think? 72%.
Oh, wow.
No.
Probably not. I would be leaning towards not, based on the fact that we have been, told that probabilities for this course should be expressed as a decimal or a fraction between 0 and 1. That's not a decimal or a fraction between 0 and 1. So let's see what your author answered for this question here. Yes. I sit corrected. All right. The bottom line, ladies and gentlemen, is normally, we want to express probabilities as decimals or fractions between 0 and 1. Okay. So we don't want to express them as percents. All right. That's just the way we're going to work in our textbook here with probabilities. So I beg to differ with that there. All right. I'm not going to give you one like that on Alex to trick you like that. Don't worry about that. Okay. It'll be obvious. Okay. All right. Ladies and gentlemen, I have a question for you. Is number 19 a probability described as a theoretical probability or an empirical probability? Number 19, at one school, 59% of the students having lunch in the union are female. So the probability of a randomly selected student from the campus phone directory being male is 4.41. Okay. Do you think that the way they computed this probability of 0.41, do you think it's based on an equal likelihood model, a theoretical way, or maybe the relative frequency way, the empirical way? What do you think? What would be your guess? If you had to lean towards one or the other. What's that?
Arrow?
Empirical?
Yeah. I
Yes.
think.
Yeah, you are correct. Because this is kind of, we don't have 50-50, male and female students at the school. And for that reason, ladies and gentlemen, we're talking about relative frequency of males versus relative frequencies of females at this particular school. So it probably would be the empirical way of having determined that probability of selecting a male is 0.41. Okay. All right. Now, number 20, would you think that this would be a equal likelihood way of computing the probability or a relative frequency way? In other words, would it be theoretical or empirical? A pool table has 15 balls labeled 1 through 15. The probability of a ball made on the break having a number less than 6 is 1/3. How do you think they maybe computed that probability? What would be your guess? Did they use the theoretical or maybe the empirical way? What would be your guess? You would lean closer to which one?
Theoretical?
Yeah, you're right. This is probably the theoretical way because we're assuming that all 15 of these balls had a what? Equal chance. Do you agree? That would be my thinking on this problem. And for that reason, because, each of these balls or outcomes have an equal chance of being the ball that experiences the break. Yeah, I would think equal likelihood or theoretical. Good. Okay, let's see here. Ladies and gentlemen, the probability of a randomly selected state beginning with the letter A is 2 out of 25. How do you think they computed that probability? Did they use like the empirical relative frequency way or the theoretical way in which each state has an equal chance of being selected? What would be your guess? Yeah, empirical, because, we only have 2 states that begin with the letter A, correct? Out of 25, that's a relative frequency. So this 2 over 25 really is a relative frequency here. And by the way, what states would those be that begin with the letter A? Maybe what? Alabama, and what's the other one?
Alaska.
Alaska. Okay. All right. Here's one, number 22. While at a casino, Catalino won 10 of the first 15 hands of blackjack she played. So she has a 2/3 chance of winning on the next hand. What would you base this probability of 2/3 on? What model? The relative frequency empirical way or the theoretical equal likelihood way? What would be your guess?
Empirical?
It seems like it would be relative frequency. I mean, because it's saying like, she won, 10 out of the last 15 hands. That's a relative frequency of winnings in the past. So it seems like, yeah, the next hand, maybe, we'll use that as a probability 10/15 chances. Yeah, that seems empirical. All right, great. I'm going to have you do now 23, ladies and gentlemen, for classwork number 2. I would like you to answer all these questions, A through G. If we roll a fair die, we will assume it's fair. One time, I want you to compute the probability for each of these events. We'll call this classwork 2. Go ahead. Do that there. I'll give you some time to Let's take a look at these here. The probability on a fair die of rolling a 4 would be 1 out of 6 chances. 1/6 would be the probability, in the sense that there's only one way to roll a 4. The probability of rolling an even number on a die, there's 3 ways to roll an even face. You could roll a 1, you could roll a 2, a 4, or a 6. These are even faces. So there's 3 ways to roll an even face out of 6 possible outcomes. 3/6, 1/2. Probability of rolling a number greater than 4 would mean that you'd have to roll a 5 or a 6, which means there's 2 ways of that event occurring, 2 out of 6 ways. 1/3 would be the probability. Probability of rolling a number that's less than 7. Well, all of the outcomes, 1, 2, 3, 4, 5, and 6 are all less than 7. So there's 6 ways of rolling a number less than 7. There's a 100% chance then that we will roll a number less than 7. What's the probability of rolling a face that's greater than 0? All the faces are greater than 0. So there's again a 100% chance of this occurring, 6 ways out of 6 outcomes. Now, question F. This question is not really ready for us yet. They should not really have put this question in this section here. Or, ladies and gentlemen, we'll find out means that we add the probabilities together, the individual probabilities together. But the problem is we would be double counting some of these events here or outcomes in enumerating these events here. The best I could do with this problem here is to view it this way. How many ways can we roll a number greater than 3? Well, that would be if we roll a 4, a 5, or a 6. That's 3 ways. How many ways can we roll an odd number? Well, that would occur if we rolled a what? A 1, a 3, or a 5. Okay. That appears to be 3 ways also, but here's the problem. If you add those 3 ways here plus 3 ways for rolling an odd number, you get 6 ways, and 6 over 6 means 100% chance of rolling a number greater than 3 or rolling an odd number. That's not correct, because when you roll this die, you could roll a 2. Do you agree? A 2 is not greater than 3, and it's not an odd number. All right. So what's happening here is, because you would view that erroneously as thinking it's a 100% chance for having 3 occurrences of this, 3 ways of this occurring, and saying there's 6 over 6 ways of this happening. That's not correct, because we're double counting some of these outcomes. In other words, the number of ways of rolling a number bigger than 3 would be that we roll a 4, 5, or 6. Well, 5's been counted already once. And to say that we roll an odd number would be saying we roll a 1, 3, or 5. Well, guess what? 5 is double counted. We double counted 5. So you would have to actually subtract off what's called a joint probability here. The bottom line is this question is ill-posed for this section here. I'm not going to give you one like this out of section 23, or excuse me, out of section 10.1. We're not ready for this one. This one is a fair game question, though. It says, what's the probability that we roll a number greater than 3 and it being an odd number? Well, the only numbers that are greater than 3 are 4, 5, and 6, but it also has to be an odd number. So that means that comes down to only rolling a 5. And it's satisfying both this requirement and this requirement simultaneously. So there's only one way to roll a 5 out of 6 outcomes. Your probability would be 1/6 here. Again, F, don't worry about F. All right, we're not ready for that problem. All right, did we get these here with the exception of F? Is this making any sense here?
Yeah, that's what I got.
Okay. Okay, let's see. Next one. Number 24. You can roll this into classwork number 2. A couple has 2 children. Find the probability that both children are girls. At least one child is a girl. Both children are of the same sex. Ladies and gentlemen, we will assume for this problem, we will assume that there's an equal chance of having a boy and there's an equal chance of having a girl. We will have to assume that for these probabilities. All right, so use the equal likelihood or the theoretical probability rule to compute these probabilities. We'll add this on classwork number 2. Go ahead and do those. The first thing you're gonna have to do is you're gonna have to clearly define what are the outcomes for your sample space. I'm gonna let you think about that and populate your sample space, okay? Go ahead, try to do that problem, think about it a little bit, see if you can do some of them. Okay, sometimes when I'm in a tree structure, can help you enumerate the possible outcomes of a probability experiment. For instance, if we call this child number 1 and child number 2, the first child could be a boy or a girl. And then if we have a boy on for the first child, we could have 2 possible outcomes for the second child, a boy or a girl. If we have a girl for the first child, we could have 2 possible outcomes for the second child, boy or a girl. By following the branches of this tree, you can enumerate all the possible outcomes of this experiment. We could have a boy and a boy. We could have a boy and a girl. We could have a girl and then a boy. Or we could have a girl and a girl. So the sample space would consist of 4 possible outcomes. Boy, boy, or a boy, then a girl, or a girl and then a boy, or a girl and then a girl. So that would be the sample space, 4 outcomes. All right, now to compute the probabilities. For A, what is the probability that both of these children are girls? Okay. Well, the probability that both children are girls would be equal to the number of ways we could have 2 girls, which is only 1 way, divided by the 4 possible outcomes. So 1/4 or 0.25, 25% chance of having both girls. Again, this is assuming that both genders have an equal chance of occurring on any birth. That's the key assumption overriding this entire probability experiment here. B, what's the probability that we have at least 1 girl? Well, that could occur if we have a boy and then a girl, or a girl then a boy, or a girl and a girl. Remember, at least 1 means 1 or more. So there's 3 ways of having at least 1 girl out of 4 outcomes. So your probability would be 3/4 of 0.75 or 75% chance of having at least 1 girl. Finally, what's the probability that both children are of the same sex? Well, that would occur if you have a boy and a boy, or a girl and a girl. That's 2 ways out of 4 possible outcomes, which is 1/2 or 50% chance. Did we get those computed properly? Is this making sense here? How we're computing these probabilities here? Okay. Does anybody watch The Price is Right? This next problem is for you. Number 25, we can roll this into classwork. We're still working on classwork 2, ladies and gentlemen. Go ahead and do this problem. The key assumption here is that when we spin this wheel, which has numbers on it 1 through 7, these slots with a number on it are of equal size. That's the key assumption. If they were not of equal size, then we would have a biased situation here. But because they all have the equal size, we would say there's an equal likelihood of any one of these numbers, 1 through 7, popping up. Okay, so go ahead. I've given you enough hints there. See if you can do A through E. We'll call this part of classwork 2. Okay. The sample space for this particular probability experiment is this set consisting of 1 through 7 as being the possible outcomes, okay? All right, now, what is the probability that we roll a 6 when we spin this wheel once? Well, how many ways can a 6 occur? A 6 can only occur 1 out of 7 ways. So 1/7 would be the probability. Again, we're assuming that any one of these numbers or each of these numbers have an equal chance of occurring on any given spin. That's the key assumption. All right, now what's the probability we basically spin an even number? That would occur if we spin a 2, a 4, or a 6. And there's 3 ways of that happening, 3 out of 7 ways. So your probability would be 3/7 chance. Yeah. I left these as fractions. If you want to turn them into decimals, you can do so. The probability of spinning a number greater than 4 would occur if you spin a 5, a 6, or a 7. That can occur again 3 out of 7 ways. That's your probability. What's the probability of spinning a number that's less than 8? Well, every number is less than 8. Okay, so that would be 7 out of 7 ways of that happening, or 100% chance you're going to spin a number less than 8. What's the probability of spinning a number greater than 7? Well, there are no numbers greater than 7 on this wheel, and so there would be 0 ways of that happening. Out of 7 outcomes, probability is 0. Making sense, ladies and gentlemen? Are we getting this here? All right. Okay. All right, I want you to roll this into the same classwork, this next problem, number 26. Now, here's what you're going to have to do. You're going to have to build a frequency table that basically has all of these different students, anthropology, sociology, psychology, and you're going to have the frequency of occurrence for each one of those type of students. Just make a little table to help you compute these probabilities, okay?
Question.
Now, go ahead.
Is it possible for us to watch you actually do one?
Well, this one here, well, I can
Mhm.
build a table. Maybe that might help. So we have our table here, and we have what, anthropology? I'm going to abbreviate these here instead of writing these big old words out here. A for anthropology, how does that sound here? Okay. For sociology, I'll use S. Sociology students, and then for psychology, I'll use P. So how many anthropology? So this is our frequency column here. All right. So how many anthropology students we have? There's 5. How many sociology? There's 2. How many psychology? There's 3. What's the total number of students that were surveyed? There were 10. Okay. So your sample space, ladies and gentlemen, is going to be, what would your sample space be? Your sample space would have 5 anthropology students, so 5 A's. You're going to have 2 S's, 2 sociology students, and it's going to have 3 psychology students. So what's the probability of selecting one of these students randomly and then being an anthropology student? So what's the probability of selecting a anthropology student? How many ways can that occur? How many ways can we select an anthropology student? How many ways?
5.
5 out of how many total students were in the survey?
10.
5/10 is your probability, 1/2 or 50%. All right, you do the other ones, B through E. Okay, call that classwork 2. Compute the rest of those probabilities. Okay. What's the probability of these 10 students of selecting at random a psychology student? Well, we can see that there are 3 psychology students of the 10. So the probability of selecting a psychology student would be 3 divided by 10. That's B. C, the probability of selecting an anthropology or sociology student would be equal to the number of ways we could select an anthropology or sociology student. How many anthropologist students do we have? We got 5. Plus how many sociology students? 2. So 5 plus 2 or 7 different ways out of 10 of selecting an anthropologist student or sociologist student. 7/10 is your probability. Now, the probability of not selecting a psychologist student could probably be computed more simply by using our complementary probability rule, in the sense that we could compute this probability as 1 minus the probability of the complementary event. The complementary event of not selecting a psychology student is to say that we do select a psychology student. So this probability is equal to 1 minus the probability of selecting a psychology student. And how many ways can we select a psychology student? 3 out of 10 ways. So 1 minus 3/10 is really 10/10. 10/10 is another name for 1 whole. Minus 3/10 is 7/10. So therefore, the probability of not selecting a psychology student would be 7/10. That's one way to do the problem, using the complementary probability rule. Another way you could have done the problem is to say, well, how many different ways can I not select a psychology student? Well, to not select a psychology student occurs how many ways? 5 ways plus 2 ways, or 7 ways, because there's 5 anthropologists, 2 sociologists. 5 plus 2 is 7 out of the 10 ways of not selecting a psychologist student, 7/10. So whether you do it that way or use the complementary probability rule, either way gives you 7/10. Finally, the probability of not selecting an anthropologist student could be done again by using the complementary rule, which might be a little easier, in saying that it's equal to 1 minus the probability of selecting an anthropologist student. Well, how many ways can we select an anthropologist student out of 10? There's 5 different ways. So this probability here is going to be 5/10. And 1 minus 5/10 is the same thing as 10/10, another name for 1 whole. Minus 5/10 is 5/10 or 1/2 or 50% chance. Or another way to do the problem is the probability to not have selected an anthropologist student is equal to the probability that we select a sociologist student or a psychologist student. Well, how many ways can we select a sociologist student? Well, that occurs what? 2 out of 10 ways. How many ways to select a psychology student? There's 3 ways to select a psychology student. So the total number of ways of selecting a sociologist or psychologist student is 2 plus 3 divided by 10. So this probability of not selecting an anthropologist student would be 5/10 or 1/2. Notice we get the same probability whether we use the complementary probability rule or we don't. Okay. But this complementary probability rule, ladies and gentlemen, comes in mighty handy for certain probabilities, which otherwise would be extremely laborious or difficult to compute. So that complementary rule is very important in hopefully some probabilities we'll be able to see in our future. Okay. All right, so we rolled that into classwork number what, 2, right? Okay, let's see if there's anything else here. Okay, let's see. All right, number 43 is a somewhat interesting problem. Just have you read it and see if you can do something with it. On a 10-question true-false test, so there's 10 true-false questions. There are 7 false questions and the rest are true. So how many true questions are there? If 7 of the 10 are false, how many are true?
3.
3 are true. If Marcus answered the first 8 questions correctly and 5 of them were false, find a probability that when he answers true for the next question, he will answer it correctly. Just read that and let it sink in your mind for a minute or so. Let's see if you can do something with this problem. Just think it over. Writing some things down on your paper help too. Just to kind of document what they give you in the problem. That comes in handy also. So on your paper, you can write down 7 questions that were false, 3 questions were true. You can write that down. All right, see if you can come up with anything for number 43. Okay, so on this test, there were 7 false questions and 3 true for a total of 10 questions. The first 8 questions were answered correctly, in which case he answered 5 false and 3 true. They want to know on the ninth question, what would be the probability of guessing, if he does guess true on the ninth question, what would be the probability that it would be correct? Well, as we've already exhausted answering all 3 true questions that were on the entire exam. And so therefore, there are no more true questions available. So if he answers true on the ninth question, okay, then there's 0 ways left of answering true out of 2 possible outcomes, true or false. So the probability would be 0. So there's a 0% chance that if he answers true on the ninth question, that it would be correct. Does that make sense, sir? Because he already exhausted all three true questions around the exam. Now, if he answered false on the ninth question, what would be the probability of getting it correct? If this happened on the first 8 questions, what do you think? It'd be 100% chance, correct? Okay. All right. So I did open up the homework in section 10.1. And get started on that. Just keep in mind here with our schedule, there's on that. I did open up the chapter 7 exam. Make sure you do the 7174 homework before you dive into chapter 7 exam. That'll be due midnight, October 28th here. Okay. 10.1 homework. I did not open that up yet. I will be opening it up very shortly. All right, but just concentrate on the 7174 and getting that quiz done. Right. And when is the chapter 7 and 10 homework due? It's not due until November 28th. That seems like a million miles away from here. Okay, but try not to get behind. You just don't want to be in a position where you are behind. Just try to stay up with the homework. That keeps you in good shape as far as what's going on with any quizzes or anything.
So, so on the quiz is gonna be on chapter 7.
7, that's right. Mm-hmm.
Okay.
Yep, that's it. Yeah, I didn't put anything out of chapter 7, 11.8. That was involving regression. I decided not to. Regression is a topic that you would cover in a course in statistics or probability, math 150 here at Mott. So I did not want to, include any of that. I don't think that's really relevant. Okay, I did want to go over it, but I'm not going to hold you responsible for it. All righty.
Well, thank you. That makes that a little bit better. This is Tamara. I emailed you. I sent on some of my homework. There was one problem that I kept typing it in on the calculator, kept getting the same answer, but the system didn't take it. And I just want to know if you can look at that to tell me
Well,
why.
I need to know the homework assignment and the question.
Yep, I sent it to you.
Oh, you sent it to me. Okay.
Yeah.
All right, I'll check into that. All right.
Okay.
All righty.
Hey, Professor, did you ever open that up or no? I sent you an email. Maybe I'm doing something wrong.
For what now? For Carlos?
Yeah.
Okay, which one was that?
Was that 5 or 6? Remember, I made a mistake and submitted it after one question.
Yeah, no. I believe I opened it up. I'll double check again. I could have swore I opened that up and gave you another chance on it. Okay, that's chapter 5 and 6 exam.
Yeah, I went in there and it got the same. I keep trying to, like push the button and
All right.
it keeps showing me the same, what I submitted before.
All right, Carlos, I'll do that in the next minute or so. I'll go back and investigate, okay? And open that up if it's closed, all right?
All right, okay. Well,
all right, try to get that done.
Well, no, I mean, I'll get it done today. But
yeah, okay, yeah, I'll give you a day or two.
Yeah, I just was just trying to figure out, like, am I doing something wrong while it's not opening up?
All right.
It just keeps showing the same thing.
All right, I'll get that open for you.
All right, okay, thanks. Okay, all right.
One more thing, quick question on the quiz. You're saying we're only being tested on chapter 7, or is it 11.8 as well?
Just chapter 7.
Just chapter 7. Okay.
That's it. All right.